Welcome back. This is the worst part of teaching in academics. It's December. Everybody just had a break. We've got 2 weeks of semester and then finals week. And I'm guessing the last thing you want to do is do new things. Am I right? Maybe not. You don't need to tell me that. You can keep that to yourself. But that being said, I always find this time of year to be the toughest. I feel like you remember the COVID year, which was first of all terrible. I feel like we stopped instruction at Thanksgiving, and then everybody like got to have their break, so people wouldn't have to come back and forth. I wish we did that every year, but yeah, whatever. Couple announcements. Number one, you 8 of you have signed up for project presentation times. There's 2 slots left. For those of you who haven't, please do sign up. It'll be next Thursday. Thank you for signing up so quickly. And the other thing I wanted to note for that is I found the last time we did this, when Vladimir was in class, I felt like students like were paying attention to other students because you learn a lot from each other and how you approach problems. And so I'd like to put up a video, but not online, but like on icon of your projects, if that's okay. So we'll present. You can opt out. You don't have to be part of the video. I can pause it. I can stop it. No big deal. But uh, just let me know ahead of time. But my plan would be to record it, but then put it through Icon where the public cannot see it. It'll be private and only available to the students of the class. And again, you can opt out of that. Okay? No public information at all. All right. Number two, the project due date. I had mentioned, I think, in the last homework, like December 13th. Well, I just moved homework five's due date to December 13th. So I was going to give you a couple extra days on the project, maybe the Monday of finals week or something like that. Anybody going to complain if the due date goes later? I don't think anyone complains about that, right? Now, you can always turn it in at any time. No big deal for that. Third, there's a class evaluation link that I will send an email about after class today to go and rate how I did this semester. I do appreciate any feedback you want to provide. I would take anything that you have to say as well. That would be useful, but I'll send that out. Number four, homework number five. It didn't. I uploaded the wrong file. Of course, I'm this comedy of errors I've made this year. I swear, I'm just bumbling through so much right now, and I apologize to you for that. The file I uploaded to have your GRI items for homework five didn't have the 2 columns in it that I thought it did. There are 2 columns on that file. Here, let me share with you what I'm talking about here. Give me just a second. And homework. So this GRI items file should have a financial and non-financial column to it. That's your Q matrix. The file online up to this point didn't have it, and I apologize to you for not having it there. Vladimir, that's okay. That is okay because it sounds funny. Um, this is a weird item. It is in both columns, and maybe that shouldn't be the case, right? It seems weird to have financial and non-financial. Those seem to be complementary and mutually exclusive. But if you look at the text of the item, oh my goodness, just a second here. Ah, open. Oh, how many allows do I have to do? All right, here we go. This item, uh, it says, "I am drawn more by the thrill of gambling than by the money I can win." I have a hard. So let me back up. Backstory on these data. These data came to me when I was in grad school. I literally collected data on a gambling boat in Illinois from gamblers, although this is sort of permutations of that data. These are the items that we asked. Um, when we originally designed this study, there were 10 dimensions, one dimension for each. So we were studying something called pathological gambling. Pathological gambling is uh, listed in the Diagnostic and Statistical Manual of Mental Disorders, DSM, as an impulse control disorder. Right? People who have a hard time stopping gambling. This was in like 2001, back when gambling was relatively minor compared to where it is now. If you watch sports, you're inundated with ads for betting apps and everything else, right? We didn't have that back then. Anyway, long story short, to try to give you a chance to do multiple dimensions, I thought, let's cut this down and think about concerns about financial reasons for gambling and non-financial reasons. Just to simplify it, it's sort of a dumb idea, but it's two dimensions. Think of it this way: like I want to give you real data, but it's two dimensions. So um, relatively uh, quicker to run to give you that experience because going from one dimension to two is a big hurdle, right? We saw that before Thanksgiving. We talked about Cholesky decompositions and correlation matrices and all these other things that show up, right? So I wanted to give you that practice. So Vladimir, you're right. I don't know what to do with this item. I'm drawn more by the thrill of gambling than by the money I could win. So I put a one in both columns. Is that a good idea? Probably not. I don't know. But how's this sound? Why do I say it like that so nonchalant? Because Lisa Hoffman likes to say that's an empirical question, right? With the one in both columns, that means you're estimating a slope or a discrimination for each dimension. And if one of those happens to be zero, won't hurt anything, right? So in some ways, when I put ones in both columns, it's almost like me being somewhat exploratory for that item, right? I have enough zeros in the Q matrix to identify my model, but this is me saying, I don't know. This could be an item that goes toward gambling, non-financial, the thrill of gambling, but it also talks about money. I'm going to go for money. So I'm looking at it from that perspective. Um, you know, from a research perspective, if you were going to go and try to publish something about this, having a better plan might be it, or acknowledging you didn't know it in the first place, and this is sort of exploratory would be fine too. Does that sound okay? And Vladimir, is that a good excuse? All right. Don't take this opportunity to go gamble though. I didn't pass IRB, and if this causes you to be having to trigger a gambling urge and you let me know, there's 1-800 numbers I'll refer you to help you with that, okay? Do you want to know the punchline of the gambling story? Probably some of you have heard this before. So we were collecting data from this casino in Peoria, Illinois. I was a grad student, never really gambled before in my life, and we had a grant from a consortium of casinos that were concerned about people gambling too much. Go figure, right? Tax write-off. And so, what part of our protocol was to go sit at a roulette table where we were actually have had access to the casino tapes to see how people would play and sit there like we were a stooge, like sitting there like we're just regular patrons playing roulette, and wait and sort of keep an eye on who's played for about 45 minutes. And if somebody were to leave the table after playing for 45 minutes, we would signal to one of our partners who'd go and say, "Hey, would you like to win some money? Come with us. We'll step off the casino. We'll go to the back offices and you can gamble more, pretend, and you can win money." And guess what they would do with the money? They'd take it and go back to the casino. Well, pardon me, as we were sitting there gambling, we needed to gamble with some money. And it turned out we were gambling with grant money. So there you have it. The best story in the world. We gambled with grant money. I'm pretty convinced the professor, the PI of the project, Larry Jones was his name, wanted that project just to be able to say, yeah, I gambled with grant money. The end. Talk about getting through IRB these days with that, right? All right. There's your punchline. Okay. So, homework 5, new Q matrix, new due date. Not due this Friday, due a week from Friday. Okay? Okay. And then finally, on Thursday's class will be a mix of whatever's left from lecture for today, if we have anything left, and any questions, comments, or open time if you'd like to talk about projects or anything that we go through from there. Okay? All right. And again, my head is turned sideways. I changed my setup a little bit here, so I'm looking at you over here, even though I should be looking here. Anyway, we good? All right. So let's talk a little bit about prior distribution, shall we? Actually, let me stop. Any questions? I think I just asked that. Any questions again? All right. I'll probably end up sending a few announcements just to make sure we're clear on anything. If anything's unclear, please don't hesitate to reach out, and I apologize for whatever lack of clarity there may be. All right. Empirical priors. You've heard me use that term before, haven't you? We used it in linear model land, if you remember. What's an empirical prior? I'll answer it. An empirical prior is a prior where the hyperparameters, one or more hyperparameters, may be estimated. Right? So think about it this way. If you have a set of factor loadings or discrimination parameters, we typically have used a prior with a mean of 0, standard deviation that we set when we run those novels, but you don't have to. What if you said, no, wait a minute, I have, 10 items on my survey, so I'll have 10 of these parameters. I'm going to say they're normally distributed, but I don't know what the mean is. I'm going to estimate the mean. And I don't know what the variance is or the standard deviation is. I'm going to estimate the standard deviation, right? Could you do that? Is it possible? Turns out it is. We have 10 items, right? And just like in basic statistics, how many observations do you need to calculate a mean, right? You need like two, actually one. You can always calculate a mean. It's kind of a dumb mean. It's the same number, right? You need at least two to have the standard deviation. I guess an n minus one might still a dumb number. Let's say 2 and 3, but you have more than that. So we can use that to our advantage. And so today we're going to talk about ways that we can build empirical priors in because they do show up from time to time. In fact, a lot of the more philosophically true Bayesians, the Bayesians who are like Bayesian by belief, love empirical priors. So we'll talk about those now. Okay. Uh, and we'll see what ramifications they have, changing prior distributions for varying parameters as we do this. We're still going to use our conspiracy theory data. You can see the questions here. But let's go back to CFA. I'm going to go back to CFA. You don't have to. We could go back. Um, we could definitely do this with a greater response or nominal response type model or a categorical model, and we should do that. But today I'm going to revert back to CFA because CFA is using a normal distribution makes things a lot more mathematically tractable. Let's put it that way, right? It's easier to see how results work because the structure of the normal distribution is relatively easy to work with mathematically. It's still a mess. It's still horribly complicated, but it makes it a little bit easier to see. So I'm going to choose CFA. Um, and the other reason for CFA is we know very clearly what minimal identification constraints are needed to identify the model, right? We talked about two of those. One is how many items per factor, right? We need at least 3 per factor. Technically, you could get away with 3 on one factor, 2 on another if the factors are correlated. Additionally, we know that we need to set a constraint on, we have to figure out how we identify the mean and the standard deviation of the latent trait, right? Up to this point in class, we've used a 0 mean and a 1 for a standard deviation for the latent trait. We call it a standardized factor. We're about to change that. All right. We're also going to go back to a single latent variable for this lecture. So we just have 1 theta, just to make things a little bit more straightforward as well, too. Next lecture, when we talk about scale identification, when we start changing the way that we look at theta, we will go and have more than 1 theta at the end. Okay? Okay. So let's talk about empirical priors for item parameters here. You see this all the time. In fact, the book that we use for this class, they use empirical priors for item parameters. It's suggested. And empirical priors are, again, a prior where the hyperparameters of the prior distribution are estimated and are not fixed. So why would you want to use that? Well, several reasons. One, you have a lot of parameters, and your choice of prior may not work equally well for all of them, right? Up to this point, we've had one constant prior, even though we made code so that we'd have a mean of 0 for each parameter and a standard deviation for each parameter, usually 1 or 10. It may be the case that it's hard to figure out what your prior needs to be. If you had 100 items, where would you set the prior? All the same, some different? So the empirical prior is a way to sort of do the least amount of harm with the prior by estimating what the mean and the variance may need to be. So, for instance, we could take our lambda parameters. Previously, we specified them to have a prior distribution with a mean of 0 and a standard deviation of the square root of 1,000. Now, however, we might just say the mean is estimate it. It's some mean that we don't know what it is. It's a parameter of our model. And there may be some standard deviation that we want to estimate as well too. Similarly, we could do the same thing with mu, right? And we could do the same thing. And remember, in CFA, we have this residual variance, or sometimes called unique variance. Now, stand in the normal distribution, it's a standard deviation. So we may go and say, wait, if we model that with an exponential prior, we may want to estimate the rate parameter it happened to be. Where previously we had set that parameter to be zero point 0.1 because that was sort of uninformative. Sound good? Now, once again, we're not including theta here, right? Theta is tough. And this makes psychometric models somewhat unique, right? You can't estimate everything all the time without making some crazy decisions. So we need theta to stay set, its prior distribution to be fixed, because that fixes the scale. And once we have the scale of the latent variable, all these other parameters fall into line. So if we tried to use an empirical prior for theta while we were using an empirical prior for every one of our other parameters, we would not be setting the scale, right? An empirical prior for theta would indicate its mean and its standard deviation, but we have to fix those because it doesn't exist. So theta right now, we're going to just push to the side and ignore it. The next lecture is talking about theta. Well, we call that scale identification. It's this weird part of psychometrics when it meets Bayes, in that theta is a parameter, it's a person parameter, it needs a prior distribution, but that has ramifications for how we identify our model. And that's part that is a little bit more nuanced than just straight applying Bayes to what we do. Okay, so for psychometric models, choosing empirical priors, though, has a few pitfalls, right? Not all model parameters can use empirical priors. The thetas can't, right? The use of such priors can make some parameter estimates move toward values that would indicate more information than for theta than what's present in the data. Okay, let's think about this. Remember, we mentioned the factor loading lambda. That thing described um, how much a latent trait was related to the item response itself. Right. So if we put a prior distribution on it that forces lambda towards 0, it makes our data requirements higher to make claims about theta, right? We'd have to have more signal in our data to come up with a good claim about theta. If we used a prior distribution where we moved lambda toward, let's say, 4 or 5, a really big number, right? We could look like our result has a lot of information for theta potentially if we don't have a lot of data. If our prior overwhelms the data, we'll end up thinking our model has a lot more information about the latent rate than we really do. So that's another reason. And then finally, this is less so in psychometrics because thetas tend to have a similar scale. But empirical priors may be inappropriate when some observed variables have widely different scales or use different distributions. What do I mean by that? Right? So think of it this way. If we put an empirical prior on lambda, going back to our model here, lambda has a scale to it. Right? We know what this is. It's units of y per units of theta. Right? So units of y implies standard deviation of y. And we know from our data y is a 5-point Likert scale. So we sort of understand what a standard deviation might be. But if all of a sudden we added an item where y was, count the number of times you believe, how many times did you look up conspiracy theories in the last week or something like that? Some variable that may have a larger standard deviation, then the scale, the numerator of the scale of lambda changes, right? It gets bigger. Those lambdas will be bigger, even just because the scale of y changed. And so because of that, an empirical prior may not really be appropriate because it may be hard. You may have some parameters for some items that have big scale, like a big standard deviation, and some items that may have a small standard deviation. And putting those two priors together may be hard. So all that said, I don't really recommend using empirical priors in psychometric analyses because to me, particularly for lambda, that thing is easily manipulated and can make a result look more rosy or better in the psychometric sense for theta just because of a model choice, not because of the data itself, not because of an empirical phenomenon. So I tend to not recommend this, but sometimes they're needed. And sometimes you read about them. So I want to tell you about them to see it. Okay? Okay. So let's talk about what we're doing here. This is our parameters model block, right? We always start with model. Remember, with CFA, we have our items. They're normally distributed. We have our linear predictor there, mu plus lambda times theta, and we have a residual or unique standard deviation also. So now let's go to each of our parameters. Theta itself, we're using a standard normal prior for it, as we have before, so we just leave theta alone. But the other parameters are where things start to change. Take a look at lambda, right? Lambda, right here, we're going to say follows a normal distribution, which we've been using through the class, with a mean and a standard deviation. So rather than fixing this prior, or rather than setting it through values that we import into Stan in the data block, what we're going to do is use this as an estimated parameter. We're going to come up with the mean of all of our factor loadings from this. We're also going to come up with the standard deviation for all of our factor loadings from it. But because mean lambda and standard deviation lambda are being used as parameters now, they need priors. And welcome to the Bayesian rabbit hole, right? We have a parameter, we put a prior distribution on. That prior distribution has hyperparameters. If we want to estimate those, we need a prior distribution on. You can keep going, potentially, right? Although I will say with only one mean lambda and one standard deviation lambda, we ran out of degrees of freedom to estimate anything else. So basically, we've put the mean lambda now, we need a prior on it, and I'm going to call that a normal distribution, where we set its hyperparameters. And I'm running out of terms for these variable names. So I literally have a variable named mean lambda mean, right? Mean lambda refers to the parameter, and mean refers to its hyperparameter of it. Okay? And then we have mean lambda standard deviation refers to this is now the standard deviation hyperparameter of our lambda mean. Okay? Those are things we're going to set and we're going to import into Stan. Similarly with standard deviation for lambda, you'll see it. We're going to use an exponential for it, distribution for it. That's the distribution we started with CFA. And it will have a rate parameter, which I call SD lambda rate. And that itself will be my hyperparameter for my standard deviation for lambda. Okay? Okay. Turns out all of what I just said for lambda applies for mu too. Right? We're going to estimate the mean of all the intercepts and the standard deviation of all the intercepts. So therefore, we need a prior for the mean of all the intercepts. That's going to be normal with two hyperparameters for its mean and standard deviation. We're going to need a prior for the standard deviation of all the intercepts. It's going to be exponential, where we set the rate hyperparameter for the standard deviation as well. Okay? Finally, last parameter is the unique standard deviation psi. We will still use an exponential with that, but now we will estimate its rate parameter. And because we're estimating that parameter, we will also need to set a prior distribution for it. And here we will have the rate parameter for that prior distribution. Questions on any of this? They're small changes, right? This mean mu, standard deviation mu, means lambda, standard deviation lambda, and psi rate. These are the new things we're adding. And each one of those corresponds to our estimated hyperparameters, our empirically estimated hyperparameters. So now, I just described all that. Excuse me. In the Stan parameters block here, we can see each of the parameters that we're going to estimate. You will note theta, mu, and lambda were there from before, and psi. But now we have the mean lambda, standard deviation lambda. Those are the two hyperparameters for lambda. The mean mu, standard deviation mu. That's the two hyperparameters for mu, or the intercepts. And the psi rate, which is our rate parameter for all the unique standard deviations. So we're going to estimate all those. And you'll note some of these have lower bounds, right? The standard deviation parameter, the SD mu, which we set here, as an exponential parameter, if you remember the exponential distribution, the rate parameter has to be positive. So one of the other catches about hyperparameters is that you still have to make sure that their what we call their support, the range of values that they can take, is consistent. So each of these rate parameters has a lower bound of 0 implied. Questions on any of this? All good. All right. Now in the data block here, we are going to import hyperparameters for the mean and standard deviation of lambda's mean, the mean and standard deviation of mu's mean, and then the rate parameter for the standard deviation of lambda, the rate parameter for the standard deviation of mu, and then the rate parameter for the rate parameter of psi. And yes, that's why it says rate psi rate. It's not Go Dog Go. It's not a children's book, although it would make a great children's book. Maybe some of you can. I started class with the Bayesian for babies. This is your chant. Go Dog Go, mean lambda mean, something like that. Anyway. All right. So in R, we just set these values. I'm going to set the hyperparameter for the mean of lambda to 0, and the hyperparameter of the standard deviation of lambda to 1. I'm sorry, it's the hyperparameter of the mean standard deviation to 1. You would think of this as sort of a strong prior, right? What is it doing? It's whoa, Jesus, Jonathan. Excuse me. Ah, come on, Jonathan. What happened there? It's stealing all the secret. It's like, oh, it skipped ahead to the end. Terrible. If your like favorite TV series did that on Netflix, if they got out of order, what would you do, right? You'd probably just quit your never mind. Anyway, or maybe you just reclaim all the time that you have and enjoy life better. Who knows? Anyway, I'm setting these to 0 and 1 because what that does is it ensures the overall mean is sort of squished to 0. And so that does put a little bit more downward pressure on the mean of lambda itself. Um, but realistically, I don't know what values to set for this. It's harder to set. I also set the standard deviation parameter 0.1. Remember, the exponential distribution with a rate of 0.1 is fairly uninformative, right? And so you can see all that. Here is our model statement. I will note in my going through my slides this morning, I actually ended up having to expand the number of iterations for sampling and warm-up, mainly because convergence issues, of course, right? This is a more complicated model. We're estimating 2 more parameters for the lambdas. We're estimating 2 more parameters for the mu, and we're estimating 1 more parameter for the rates of the size. So it's more complicated. It's going to be a little bit harder to get to converge quickly. More complicated models tend to take longer, more iterations. All right. Before we show the results, I did want to make a little connection here. Empirical priors are like multi-level models, right? Um, there's a whole world of multi-level measurement models out there. I don't know if you've seen those before. If you haven't, my YouTube channel, Lisa Hoffman and I gave a workshop on it a couple years ago in Germany. Actually, we're going to give another workshop in Germany next year. Maybe you can join. Come to SMIP in Germany. Um, Point being, each of these parameters, though, if you think about it, lambda, if you say lambda follows a normal distribution with a mean mu and standard deviation sigma, we could actually reparameterize that a little bit to say that lambda star is equal to mu plus some error, where error follows a normal distribution with some sigma, with a sigma here. So what I'm trying to indicate here is that by building empirical priors, you're doing 2 things. One, you're not having to specify hyperparameters for every possible lambda. But number 2, you are actually building almost like a multi-level model. And furthermore, if you think about multi-level models, often what we want to do is predict a parameter in a multi-level model with a series of predictors in this linear function. And you could do that too. Turns out you could put in predictors for lambda. You could even do the same thing for mu. By the way, if you're hearing noise, I apologize. I'm having We're having some contractors in at the house, and so I'm hearing drilling. So if you hear that, I apologize. But I'll do my best to persevere. Um, Focus, Jonathan, focus. The drill will go away soon. Um, for mu, same thing will happen, right? We could say mu follows this. What predicting each of these will do will shrink the residual variance, or you could call this almost like a residual or almost like a level two variance of each of these parameters. And when you do that, there's a whole class of models that we don't talk about in most of our classes, but are really useful. And actually, a lot of the research I'm doing these days sort of involves. These are things that are called explanatory item response models. What we use for explanatory item response models is that we basically say, you know what, each parameter of our model, if we look at our CFA model right here, every item gets their own lambda and every item gets their own mu. In an explanatory IRT model, what we say is, no, not everybody gets the same mu and lambda. It'll depend on what predicts mu and what predicts lambda. So basically, we're trying to predict what mu and lambda will be through a series of features of each of the items themselves. Those features may include, you know, content of the item, length of the item, anything, almost anything item related will go there. But explanatory IRT models are incredibly useful. I think they're going to become even more useful as we see large language models or other AI tools start to create items for us where we may have an infinite item pool or semi-infinite item pool, because otherwise we'd have to go and get data on every item to get its own parameters. An explanatory model can sort of bridge that a little bit. So that's another connection. The other thing I wanted to make, I didn't note the rate here. You could actually come up with a rate version of like a hierarchical rate parameter, but that's trickier. But we can do that. We'll just leave it off. So the other thing I wanted to mention is the terms. We can call these explanatory item response models. We can call this multi-level model. But in Bayes, we call this hierarchical Bayesian. It's hierarchical Bayesian because we have a model parameter lambda. It has a set of priors, empirical priors, and those empirical priors have priors. So it's these hierarchy of priors that we have here. So a lot of times we call this hierarchical Bayes. Questions on any of this? All right. I know this is super exciting, right? This is why we have this class on Tuesday morning, because if you put it at night, you wouldn't sleep all night. It would be that amazing. All right. Hang on a second here. Let me recompile. You want to work. You can do it. Okay. There we go. Nope, we don't go. All right, let's see what we've got here. All right, so if we were to run this model, right here, I'm bothered because I have a convergence result of 1.52. Oh, I know my problem. I didn't save my image. This, by the way, is if you ever teach this class, recompiling models and doing things like this takes a lot of effort. So I didn't save my result and then recompile it because running this code took 15 minutes and then recompiling takes another few moments. So just a moment, we'll have it up here. Now we have it. No, we don't. All right. Well, we're going to look at model code then because something I'm doing is wrong. So here, ignore the slide. Let's take a look at the model code. The maximum value for convergence here, actually, we're at CFA model 2 here. Our model 2 result looks like this. And when I print the item parameters, they look like this over here. So ignore what's on the right-hand side of my screen. In fact, I should just do this like that. Make this a little bigger. But here you can see our maximum R hat is 1.002. Now let's take a look at some of these parameters I think that are somewhat interesting here, right? You can see all of our mu parameters. Those are estimated fine. The overall average mu turned out to be 1.87 with a posterior standard deviation of 1.02. That seems reasonable. What does that tell us? The average intercept for an item is 1.87. And because this is a CFA model, what that means is for a given random item, When theta equals 0, the average rating is going to be uh, just about the disagree level, right? Right? Strongly disagree would be a 1, disagree would be a 2, and 1.87 is pretty close to 2. So that's the disagree level. Cool? That's for an average level of theta, theta at 0. The standard deviation of that turned out to be 0.242. So you can think about where that range might be, plus or minus, and that's for the mean. For the lambdas, similarly, our mean lambda was 0.817, and our standard deviation was 0.08. You'll see that that standard deviation is smaller, but again, the scale, the range of these values is smaller as well. And that seems reasonable, right? So that's telling us the average factor loading was 0.817. And finally, the psi rate parameter right here is 1.56. Excuse me. Remember, psi, the rate parameter for psi, that is the exponential distributions parameter, right? It describes sort of the distribution of our this positive, weird, skewed distribution, and it's kind of hard to interpret, right? And so, if we were to try to look at it, if I quickly grab some help here, the exponential distribution itself, um, the rate lambda is here, and actually, if we were to try to describe what it happens to be, we'd have to go back to the distribution definition. We know the mean is 1 over lambda. So what this rate parameter is telling us of 1.56 is, if we take 1 over 1.56, that'll tell us that the average residual standard deviation, or the average unique standard deviation, is 0.64. That's what it's telling us. We also know the variance is 1 over that squared. So if we wanted to talk about it's the variance of our residual standard deviations, it's 0.41, or if we really wanted to make it understandable, the square root of it would tell us, well, it's the same number. Mean and standard deviation the same. Come on, Jonathan, use some math. All right. So, does that make sense? Our um, our values here are just describing where those parameters may be. But now let's talk about comparing them. All right. Um, Sorry for the typo. 2 lambdas is kind of interesting. Lambda lambda. Um, Sounds like the most terrible fraternity or sorority we've ever had. Lambda lambda. All right. This is a plot of running the same model where I had the uninformative non-empirical prior. So this is the prior that we started class with versus the empirical prior that we just put on. And what stands out to you here? Does that look pretty strongly correlated? In fact, if I really wanted to get the correlation, our correlation happened to be 0.995 between our parameter estimates. So, what's that tell you? Mostly the same, sort of the same, but I want you to take a look real quick. The scale is somewhat different. Okay? In the uninformative prior, the range that you see on the x-axis goes from a little bit below zero point 0.7 to a little bit of right about 1, right? On the y-axis, the range goes from a little bit below 0.75 to right about zero point 0.9. Why is that the case, do you think? Why are they different? Let's take a look. In our original model, we specified the variance of lambda to be 1,000, right? And so, oops, oops. That means our standard deviation was 31.6 as a hyperparameter, right? So wide, very big standard deviation for prior. In our empirical prior, though, we estimated what that value happened to be. And our estimate for our lambda standard deviation happened to be 0.08, narrow. So what's happening is that the range of the prior estimates are being shrunken, right? Remember in Bayes, the prior may shrink our parameters toward a mean, right? It's shrinking the values of lambda toward the hyperparameter of the mean, which is 0.817, right about here. So what's happening is this model is condensing the range of lambda because of its prior being estimated. We didn't set it, we estimated. Interesting, right? All right, let's talk about this is the difference between our uninformative prior, the estimate, the EAP estimate of lambda from our uninformative prior, if we subtract from that our estimated lambda from our empirical prior. So anything negative means our empirical prior is bigger. Anything positive means our uninformative prior's lambda is bigger. And you can see we have a little bit on both. Just it looks like uninformative lambdas are a little bit bigger. And we saw that in this plot because the range of the uninformative lambda was a bit wider. Now we can do the same thing for the standard deviations for lambda. This is the posterior standard deviation. So now these are the values of the posterior standard deviations that you see here. And again, you will see that in the uninformative prior, our posterior standard deviations are a little bit bigger also, right? In fact, here, you'll see it. Most of those are positive. And that's because the difference in our hyperparameter. When we fixed the hyperparameter, the standard deviation was 31, very uninformative. When we estimated, the standard deviation was 0.08, very, very informative. And so that effect shows up on the posterior standard deviation for lambda, right? So let me ask you a question. Which is more appropriate? Which is right? Who knows? It depends on your belief. I know that sounds terrible. What we could do? How would you try to answer that question? Model fit. Very good. Thank you, JC. Model fit. Yes. Right. So that is lambda. We can do the same thing for mu. Similar trend, right? Very highly correlated, but the range is slightly different, right? And here you'll see the difference. We tend to have more bigger, bigger, more positive mu in the difference. So our uninformed prior, the mu is a little bit bigger. So you can see that a lot of what mu is doing is shrinking it a little bit smaller. And then the posterior standard deviation, the similar trend happens in our uninformative prior. Um, Actually, this is a little bit weirder. Yeah. Okay. And then we have our rate parameters here. Same thing happens. Here's our difference. And our posterior standard deviations as well. Now let's talk about theta, though. What's the impact on theta? Here's our plot. Does that look like impact on theta? Not really. And in fact, here's the difference in EAP estimates. Very small. There is a difference, though, right? There is a difference. So technically speaking, our posterior distributions for thetas are different, but are they meaningfully different? Probably not. And within the context of each model, the order of theta is the same. Nobody's theta is getting out of order. Everybody's in the same order that you had before. It's just the actual values themselves have changed. So if you think about what this means from a practical point of view, if you're giving scores to people, the choice of informative versus uninformative probably doesn't change the ordering of scores. Now, if we look at the standard deviation of theta, that does change a little bit. However, what you'll see here is that our uninformative prior for theta tended to have a smaller posterior standard deviation than our empirical prior for theta. And this is an interesting finding. Maybe you find it trivial. It's not that big of a difference. But what's interesting about it is part of the this is happening is that we're estimating hyperparameters for our lambdas and for our mu's, and even for our size, which causes a little bit of wiggle or estimation error in each of the parameters themselves. And that leads to having a bit larger posterior standard deviation of theta, just a small bit, because we have these extra parameters we have to estimate. So it's an interesting world with the empirical priors, at least to me. Anybody interested by this? How many of you want to use empirical priors? You have my permission. Just because I don't recommend it doesn't mean you don't have a reason to use it. So, not that you need my permission. Maybe you do. If you're worried about your grade on the project, don't. I'm going to grade it fairly. But if you used empirical priors on your project, totally cool. Just define why. It could be as simple as I didn't know what to set, so I let the data try to figure it out. Okay? Okay. What about empirical priors? Yes, Vladimir. Hmm. Yes. Right. It's informative, much more informative than 1,000, clearly, right? Because it's much smaller. However, it's for a different parameter, right? I'm putting this hyperparameter on the mean lambda itself. The mean lambda summarizes our lambda parameters themselves. And let's take a look. Would you like to see what would happen if I changed it to be less informative? I'm going to tell you why. I'm going to tell you why I did it, and I'll try to play with it to show it to you. I set this here because think of it this way. Lambda is a slope that multiplies theta. But theta is not being estimated. I mean, sorry, theta doesn't exist. Right? So we have to estimate theta. That means lambda is going to have a hard time because theta is always moving around for everybody, right? So if lambda has a hard time, guess what the mean's going to have a hard time for, right? If we can't figure out where all the lambdas are, the mean of all the lambdas are going to have a hard time to be estimated as well. So what I'm saying is we start to move further and further from the data, right? Our hyperparameters tend to need to be stronger to be more informative because the parts that we're estimating are estimates themselves. And those estimates have a lot of error to them. All right. So let me just change it a little bit to try. What number would you like me to put this to? Like 1,000? Like that? How about I do the same value of the standard deviation we used before? How's that sound? Now let's see what happens. By the way, between the last couple of weeks, I did get a brand new computer here, so that thing flies. I love it. Got an M4 MacBook Pro. Super excited. All right, it did converge. Let's see what happened. All right. So here, our mean was 1.88. Our standard deviation was 0.243. And let's see if I still have the previous results. Previously, it was 1.87 or 0.187 and standard deviation 0.08. So you'll see it did converge. It did. Um, the mean was slightly larger, right? It wasn't shrunken towards zero. The standard deviation was what, zero point zero 0.08 versus what was it up here? 0.08. So it didn't really make a difference. So that's actually beneficial. Um, so yeah, my hunch was, my speculation was I'd need a more informative prior on empirical as you move higher. But in this case, yes, it didn't really make a difference. So there you have it. Thank you for the question. Other questions? All right, let's go back to theta then. I don't understand why I have theta theta here. Anyway, I'll try not to be bothered by it. Excuse me. It's like on every slide. I know I haven't made that many typos. That's some weird markdown or Quarto thing. I'll have to figure that out later. All right. So if empirical priors can work for item parameters, Can we use empirical priors to estimate the mean or standard deviation of our latent variable, theta theta? Should just be one theta. In short, no, right? Because we have to fix the scale. So if we put empirical priors to the mean and standard deviation of the latent variable, that's like saying we don't have the scale. We're going to let the data figure out the scale, but there are no data. Theta, it doesn't exist. We have to create it. So we've set theta's priors to a mean of 0 and a standard deviation of 1 throughout the class. In just a moment, we're going to change that. But here, let me just show you some results of what happens if I tried, right? I say no syntax, but there is syntax. I actually have syntax right over here. Let's move in and put a prior mean for theta here and a prior standard deviation here and estimate it. All right. When I do that, I don't see it here. Let's go to my results. Let's hang on one second here. Mean theta and standard deviation theta are at top here, but you'll note my R hat 1.46. That's your first indicator something's wrong in this model. 1.46 isn't good. All I did was add those hyperparameters, and you can even see my mean theta mean is 0, my mean theta standard deviation is 1. Now, I will say if I modify these to make it super informative, guess what I'm doing? That super informative hyperparameter is like setting the mean and setting the standard deviation. So in theory, you probably could go and do that, but just set the mean and standard deviation because it's better. Here's our Markov chain for mean theta and standard deviation theta. It's pretty bad, isn't it? All right, what if I went and fixed priors on everything else, right? So here, what if I fit a prior distribution to be much more informative, lambda being standard normal, psi being exponential. I'm sorry for all this double printing. I don't know what's going on Quarto here, so this is a problem. And if I do that, you can see I still don't get convert. I get a little bit better, right? I have an R hat of 1.22 for the mean for theta and 1.08 for the standard deviation. I'm still not good though. So not cool. Theta, when you mess with theta, you mess with the scale, and that's the weird part about the Bayesian psychometric model. That theta parameter has to you have to fix it. You have to have a scale somehow. And there's your plots for it. So, questions on any of this? Let's then stop here and